The nice thing about the chi-square test for independence is it's going to be the same mechanics as the chi-square test for homogeneity. Everything is basically the same. The only difference is our null and how we write it and our alternative. So again, we are going through just the mechanics of phantoms minus the p, the chi-square test of independence. So if you remember with the goodness of fit test, we are looking at one population or group over one categorical variable. And with the test for homogeneity, we are looking at two populations or groups over one categorical variable. So we were looking and comparing, are these two groups the same? Now we are going into chi-square test of independence, where we are looking at one population or group again. However, unlike goodness of fit, we are now comparing it on two categorical variables. So goodness of fit was just one categorical variable. And with these independence tests, we often deal with something called a contingency table, and basically, the counts are organized in a way where they're intersecting, signaling that this person has both qualities. The only reason I kind of throw this vocabulary in there is because sometimes they do like to include it in questions. So I don't want it to be something that you feel unfamiliar with. So, a test of whether the two categorical variables are going to be independent. So, that's basically what we're asking. Are they standalone categorical variables, or is there some type of association? So, it examines the distribution of counts for one group of individuals classified according to both variables in a contingency table. So, we're trying to see, is there some type of association between categorical variable A and categorical variable B? So, the big change between this test and homogeneity is the hypotheses. So, we are going to compare categorical variable 1 and categorical variable 2, and we are going to say in the null that they are independent, meaning they have no association for whatever population or group we are talking about. For the alternative, we are going to say they are not independent, or there is an association for population or group. Now, here it's very important that we do not say dependent. I know that's what our brain wants to do automatically. However, we'll kind of talk about it in just a second, but based on our observation and based on it just being a hypothesis test, we don't have the backing to say one variable is dependent on the other. We only can say that we have enough evidence to say it's not independent. So be careful with that, because that's something that they will dock you for on the AP exam. We're always going to say independent, not independent. And of course, you always have the option of saying no association and association. I'm going to use both options on either question today for our examples. Either one works. The only big mistake we often see is students will sometimes say dependent in the alternative, not something that you want to do. Now, assumptions and conditions are going to be exactly the same. Again, first, before you even begin any of these tests, you are going to want to make sure you're dealing with counts. Only way these chi-square tests work is if it's with categorical data. And then we are going to go in and check our randomization, our 10%, and our expected counts conditions. These are the three we've been doing so far for all chi-square tests, and it's the same three that we are going to carry on in the test of independence. And one thing to remember again, now that we are dealing with a not necessarily an experiment, but I do still like to put it in here because we do have some type of two-way table. They often can satisfy the randomization condition by randomly assigning treatments, and we can assume independence among the individuals in the study. Now, that's different from the independence overall of the test, because that's between the variables. The independence for the 10% condition is just is us just saying that each person stands alone. One result does not necessarily affect another person. Now, again, we calculate expected frequencies the same way, row total times column total over table total. However, this is something where we do it in the calculator. We don't necessarily go through and manually calculate every single expected frequency. The only time I recommend that is when you are doing a multiple choice question and they specifically ask for one single cell or one single column. Even then, it might be quicker for you to type your data into your calculator and run the test. However, that's probably the only time I would use this formula is if it was just for calculating one cell. If I'm running the entire chi-square test of independence, I would run the test and then go look at the auto-populated matrix B. And another key difference is its different name. The name is the chi-square test for independence. The chi-square test statistic is calculated in the same way, which is why we do move to the calculator, because finding the summation of the counts for all cells does take time. And the degree of freedoms is also calculated exactly the same way. Number of rows minus 1, number of columns minus 1. Again, this is something that your calculator will give you when you run that chi-square test. Calculator steps are going to be the same. We are going to enter in our observed values into matrix A, and we are fortunate enough that the calculator is going to auto-populate matrix B to include all of the expected values. So you're welcome to calculate them yourself and plug them into your calculator. However, as soon as you run that test, it's going to override and it's going to automatically calculate them for you anyway. So matrix A, matrix B, and then you're going to go to stat tests C, chi-square test, and it's going to ask, where are your observed values? Where do you want your expected? Typically, you're not going to be changing these because you're really only working with one data set at a time. Calculate, you're going to want to record your chi-squared, your p, and your degree of freedom on your paper, just to make sure that if this was the AP exam and they're being nitpicky, that you get full credit for running it through your calculator. That's kind of the move everyone has made in the last couple of years, is calculator is fine as long as you write all of the information that has been generated from it. For the note that I have, we did kind of favor the option of looking at matrix B by just going to the edit menu. So rather than going in and actually pasting it into your main screen, we found that it's easier to see all of the values when you're going to second matrix edit and then just selecting the matrix that you've told where you want the expected values. It just makes it easier because your calculator gets really weird. As soon as you click off of the matrix in the main screen, it doesn't let you scroll anymore. Weird bug that it has. And the conclusion is the same as it has always been for any hypothesis tests we've done so far. Since our p-value of whatever your p-value is, less or greater, we either reject or fail to reject the null. There is or is not convincing evidence that, and again, brief reminder, we are talking about the alternative hypothesis in context. Now, one thing I do want to really highlight here in the test of independence, because this is one area where the results often get mixed up. You have to remember that association is not causation. Just because we may come to the conclusion that these two categorical variables are associated, that does not necessarily mean one is causing the other. So a small p-value is not proof of causation. Now, the reason why I really highlight this is because often in multiple choice questions, they like to ask you, based on this hypothesis test results, do you say that there is an association, or that categorical variable A is causing B? And they try to trick you and they try to get you to agree with them. However, just because these two things are associated, again, does not mean that one is causing the other. Now, there is a couple of things that could be involved. We could have lurking variables that are causing our results to occur, and we have no real control over the data. We have no control over outside factors. And that's kind of why we can only say they are independent or they are not independent. Now, with the chi-square test in particular, it runs symmetrically, meaning it does not matter if my rows are A and my columns are B. If I flipped it, I'm still going to get the same results. So that's why it does not necessarily matter. And we can't say that they are causing one another, because if I flipped it, I'm still going to get the same thing. So just make sure you have that very clear, because it does show up often on the AP exam where they do try to trick you and tell you one is causing the other. We can't necessarily come to that conclusion. We can only come to the conclusion of association. Now, let's go ahead and run through two examples. And again, all of this is going to be exactly the same as it was with homogeneity. We're just going to name it differently, and we are going to write our hypotheses differently. So, Andrew thinks there might be a relationship between angry students and GPA. He asks, do students who are prone to sudden bursts of anger have lower GPAs? He took an SRS of 320 RHS students at the beginning of the year. He had each student take the Spielberger Trait Anger Scale test, which measures how prone a person is to sudden anger. At the end of the school year, Andrew collected the data on student GPAs. Here are the results. So, first thing that I notice when I look at this question is I have one population. I only have one group of RHS students. So, automatically, my brain is going to either it's a goodness of fit test or it's an independence test. If I had two populations, that's when I think homogeneity. So with one population, I am now looking at a two-way table. So if it's a two-way table, that is going to lead you towards independence, because I'm looking at one population over two categorical variables. So I know that's the big question I get all of the time. How do I know which test to use? Try to kind of decide early on what you're working with. One population, two categorical variables, and is this an experiment or an observational study? Well, Andrew isn't really imposing any treatments on his subjects. He's just asking a survey question. Yes, you are introducing the survey into their life. However, you are just collecting data. This is just an observational study. Now, another key giveaway for independence is they will actually use that language in the question. So they'll either say, are they independent, or is there an association? Are they not independent? So, does the data provide convincing evidence of an association between anger level and GPAs at RHS? So, again, another call back to my two categorical variables, anger level and GPA, and it's specifically asking me if there is an association. That's your giveaway. Independence automatically. So let's go ahead and get started. I'm going to write my null and my alternative. Remember that the null is that they are independent. The alternative is that they are not independent. So anger level and GPS are independent for RHS students, or anger level and GPS are not independent for RHS students. And again, you could replace this with no association and then there is an association. I do that in the next example just so that you can see both ways. So I went with independent first. And once you have your hypotheses written, you're going to move down to your assumptions and conditions. So, first two are pretty easy and straightforward. We are just stating that they are an SRS, which it was stated he randomly collected a sample from RHS students. And we are going to assume that there are at least 3,200 RHS students, which does seem fair because his sample was 320. We multiply that by 10. Now, again, I always personally write out my expected matrix and leave it blank. The reason why I do this is so that I know to come back and fill it in. If you don't have any kind of signal to come back, trust me, you are going to forget. I like to do it just so that I do not make that mistake. So I have my three conditions. I don't know necessarily if the third one is satisfied yet. Either way, in a real setting of the AP exam, they would expect you to go on. So even if the third condition happens to fail, all it would change is I would add an additional sentence in my conclusion the stating that I one of the conditions failed, therefore my results may be inaccurate. Now, method, chi-square test for independence. And now we are going to go to our calculator and we are going to plug in our values. So I am going to walk you through that. You can follow along or you can have your calculator handy and type it in as we go. First thing you do have to identify is what are the observed values. So I'm going to scroll back up to my table really quickly, and this is nice because I don't have any rows or columns for totals. If I happen to have those, you have to remember to be careful and not include them into your observed values, into what you're introducing into matrix A. So I'm going to open my calculator and I'm going to try to pull my data so I can see it side by side. Oops, nope. Let's see if it'll work. There we go. Somewhat. Okay, so I have my data, I have my calculator. So when you're entering in your data, you're going to go to second, and then this little X inverse button. It says matrix right above it. Oops, my second button didn't get hit. There we go. Now you should be in the matrix menu, and in order to enter data into the calculator, you're going to go over to edit, and typically you are editing matrix A. You're working solely in matrix A and matrix B. So I'm going to go ahead and hit enter for matrix A. And if I look at my table, I have 1, 2, 3 rows and 1, 2, 3 columns. So I have a 3 by 3 matrix. And then I just go in and type in my data exactly as it looks in my table. So I have 4, 14, 37, just double checking my values. Always important, 142, 33, 3, 79, 7, and 1. And once you have your observed values entered into matrix A, all you have to do is go to stat, over to tests, and we are going to test C, which says chi-square test, enter, and you should not have to change anything. Observed is A, expected is B, and then you can go down to calculate, and it's going to give you my chi-squared value, which is very large for this one, and my p-value, which is very small. Do not get confused and write p-value is 6.12. P-values have to come between 0 and 1. So anytime you have anything greater than 1, or you think you have anything greater than 1, should be a red flag. It's times 10 to the negative 42, which means this is like 0.00000 continuously on 41 times. Essentially, it's 0 and my degree of freedom of 4. So I'm going to record all of these values onto my paper. Generally, I like to record them now because then I won't have to go back and run the test again after I write my expected values down. So I wrote my chi-squared, my p, which I said is essentially 0, and that is okay, especially when it's times 10 to the negative 42. I will always write it out if it's like 10 to the negative 5. Anything past that, I say it's essentially 0. Now, once you have your three things recorded, you are going to want to go in and enter in your expected values. So I'm going to go back to that matrix menu. So second, X inverse. And then I'm going to go over to edit. And notice now I have matrix B populated. and it's the same dimensions as matrix A. That's because my calculator filled it in for me. So I'm going to go down to matrix B, and I have all of my expected values. The rounding on this is not as picky as it is for like our chi-squareds and our p's. So I typically just write down what I see. Gonna pull back up so you can see it a little bit better. And I just write my expected values down. All of my expected counts are greater than 5, so that condition is satisfied. So I'm going to move on to writing my conclusion. Since the p-value is essentially 0, we reject the null. There is convincing evidence that anger level and GPA are not independent for RHS students. Again, make sure that you do not say that they are dependent. They are not independent. You also could go and say they are associated, but don't want to say that they are dependent. Expected values, you're going to go, let me pull my calculator up really fast one more time. Second, X inverse, over to edit, and then I just go down to matrix B, so number 2, and they should be auto-populated there, but make sure that you have run the test. If you do not run the test, they will not show up. So you actually have to go in and do stat test C, calculate, and then your calculator will fill it in for you. Otherwise, it will remain blank or it will be values from another question. You just have to make sure you remember to run the hypothesis test. So I'm going to give you a little bit of time to copy this down, and then we will move on to example 2. Okay, let's go ahead and look at example 2. Is your index finger longer than your ring finger? Or is it the other way around? It isn't the same for everyone. Shocking, I know. To investigate if there is a relationship between gender and relative finger length, we select a random sample of 460 US high school students who completed a survey. Now, the results are shown in the table. So, again, I like to kind of walk through how we know this is an independence test. Now, it doesn't give the language in the original section, the first paragraph of association. However, it does ask if there is a relationship. That's kind of the same way as saying, is there an association? And I notice I have 2 categorical variables and I have 1 population. That is a big key giveaway that this should be an independence test. And when I go on to the actual question portion, does the data provide convincing evidence at the zero point 0.05 significance level of an association between gender and relative finger length in the population of students who completed the survey? So, again, they did give us that language of association, big giveaway, but you can kind of decipher from what do I actually have to work with. 1 population, 2 categorical variables. So I am going to, and don't get confused by the fact that it may look like I have 2 populations because I have males and females. That's not where you're getting your population from. It's from what did they sample. Now, if it said they sampled 200 males and 200 females, that would be considered 2 populations. They sampled 1 group and they just asked them the question of what is your gender. So, key difference there. Let's go ahead and write our hypotheses. Now, this one I did write with association in mind. The null is the relative finger length and gender are not associated for US high school students. And the alternative is relative finger length and gender are associated for US high school students. Either method, whether you use independent or whether you use associated, is valid. Both of them work. A lot of people like to move and write in terms of association just because that's usually how it's posed in the question, but whatever works best for you. Just make sure that you are making the null state that they are not associated, that they are independent of each other. That's the big important thing. Now I'm going to go ahead and write my assumptions. Random sample is stated and assume at least 4,600 US high school students, which is absolutely fair. There are definitely that many in the US. And again, of course, I like to write a matrix for my expected values so that I know I need to come back and fill them in. Going to name my test, chi-square test for independence. And this is where we will generally move to the calculator just so that I can get those chi-squared, p, degree of freedom, and my expected values from the calculator without having to do all of the algebra myself. So I am again going to open up my calculator. Gonna try to do split screen again, see if it works. There we go, getting a little bit better. And I'm going to go, I personally have already entered in my data into matrix C. However, you most likely will just be editing matrix A. So you would just go to edit, A, change this to, if I look at my table, it's no longer a 3 by 3, it's a 3 by 2. So I would change my dimensions to be 3 by 2, and it should automatically adjust in your calculator. And then you would go in and change all of the values to match the table. I'm going to double check that my matrix C has the correct values. So 85, 73, 42, 44, 100, and 116. That's usually an important step because sometimes we will type 10 instead of 100, and it really messes up all of our values. So I go ahead and I'm going to run my test. So stat tests, I'm going to go up to test C. And for me, I'm going to go ahead and change this to be matrix C. So if you are going to adjust your data in this way, all you have to do is hit second matrix and then in the names area, you just type whichever one you're working with. I'm not even going to change the expected matrix because it's going to fix itself. So I'm going to have my observed in matrix C, but I want it to put my expected values into matrix B. And then I'm just going to calculate. And I get my chi-squared, I get my p value, and I get my degree of freedom. Now I'm going to go in and get my expected values. So I'm going to go to second matrix, over to edit, and notice now my matrix 2 has the same dimensions as matrix C. And there are my expected values for my example 2. So I'm going to go ahead and go back to full screen, going to show my expected values, and all of them are greater than or equal to 5, so I do not have to write anything in my conclusion about this condition failing. Since the p-value of 0.3561 is greater than alpha, we fail to reject the null. There is not convincing evidence, there's an evidence missing there, that relative finger length and gender are associated for US high school students. So I'm going to go ahead and add in evidence. There we go.